Let's start with understanding the differences between neighbors and topology with our known space real numbers. For a neighbor, we need an element, which we are going to get the neighbors. At neighbors we don't care about endpoints. In fact, we don't care about any numbers except 0. But at topology, we care about every element of our open set. Yes, every element of tau is called as open set. So every open set's an R. We can't afford to have endpoints. We already seen enough reasons why that set can't be a neighbor for endpoints. Since topology care about every point of their open sets, endpoints aren't allowed in open sets. But at neighbors, endpoints present or not, they don't care. Wait, why we are getting open sets containing 0 for topology? Topology don't need that, so any open set without 0 also can join the party, even empty set. But for neighbor of 0, we don't have any set which doesn't have 0. That's the first axiom for neighbors. Next, for open sets, we can have many weird sets by unioning these sets, like unioning sets of all kinds of 2n, 2n plus 1, for all positive n, that is 2, 3, union 4, 5, union 6, 7, and lot more. Arbitrary unions allowed them to do so. These are the weird things topology does. Let's see what kind of weirdness neighbors brings. They can actually have anything, after completing the basic points process for 0. Now let's have a random set which is not open. First we have points like 1, -1, 2, -2, and so on. Then we have 0, 1 by 2, 1 by 3, 1 by 4, and so on. Then we have 1, 2. We can clearly see all elements in 1, 2. This set is a neighbor for them. That's a one kind of showing for which of the points this set value to them. Instead, we can tell topologically if a point has value in the set. That is, if a point has enough basic points inside the set, we can call that point as interior point. If every element of a set is an interior point to that set, then automatically that's an open set. By defining this, we can discuss any subset about their values in topology. If a set has enough basic points for a point, then that set is a neighbor for that point. But in topology, we can't conclude anything without discussing about other points. But now we can say that point is an interior point to that set. Here every point is interior to the set closed 0, 1. Except 0 and 1. How can we say 0 is not an interior point? Because there isn't a set A, B containing 0, which is contained in this set. But except 0 and 1, we can find A, B set containing respective point, which is contained in 0, 1. So the collection of all these A, B play an important role in this topology of real numbers. These collection helps us to identify the interior points of any random subset of real numbers. Topology collection also do the same, but it has too many. It has every possible union of these A, B's. Similarly, on a subset of R2, we can say whether an element is interior or not by these disks. If we can find such a disk for an element and contained in this set, then that point is an interior. If such disk can't be found, then that point has missing basic points in some direction. So the collection of all such disks helps in this space. This is a collection of all disks centered at every point of R2, with radius of all positive real values. But why just disks? Take any random 2D shape. This can also satisfy our requirements. We can shrunk enough that shape to tell a point interior or not. This can play same role that disks played. We can also find a specific equation for this shape too, like we had for disks, but that's not the problem here. Understanding these shapes provide same value as disks is important. So set of all these shapes with all sizes will do the trick. These shapes helps us to identify interiors on an arbitrary subset, so a subset is open if all elements are interior to that set. Hence any open set, there is a shape contained inside the open set with respect to every element of that open set. So every open set of R2 can be written as union of these shapes with respect to the elements of that open set, so these collections of shapes simplify the topology of R2. Now our goal is to define this kind of set for an arbitrary topological spaces. This collection of sets is a subset of topology, because we get some important elements from topology to define all the elements in topology, like we get disks or 2D shapes from topology of R2. These shapes will tell us set open or not, so now we are going to get a collection of subsets from an arbitrary sets, and we check whether that collection can generate a topology. First we must be clear about generating process. By generating I mean unioning arbitrary sets from this collection, that is we get a subset from B, and we union all the sets in that subset. That's what I mean by arbitrary unioning sets from this collection. Empty set is also a subset of B, so unioning elements from empty set will produce empty set. By this we get empty set on a generating process. So we have to distribute the axioms of topology to this collection. It's clear that empty set and arbitrary union will be available by generating process. Remaining we need whole set and finite intersection. By disks in R2, we mean all disks centered at all points in R2, so every element in R2 will be in at least one disk. So include that as an axiom for this collection. By this axiom we will get whole set in generating process. Remaining is finite intersection, so intersection between two elements in this collection also must be in this collection. But in the disks collection, intersection between two disks is not a disk. But we can write that intersection as union of disks. So we must use that as an axiom. But we may have doubt, does this generating process have finite intersection? Let's find out. Let's have two generating sets. Each generating set is denoted by a subset of B. We have to prove that this intersection also can be produced by generating process. For that we must need a subset of B. Unioning those elements in subset must produce this intersection. By distributive law, this will become unions of intersection. By second axiom, each of this intersection will have a subset of B. Unioning these elements will give this intersection. We can get the subsets for each intersection. Unioning these sets will give another subset of B. In this subset we have all sets to generate each intersection, so if we generate by this subset, we will get all of this intersection. Hence intersection between two generated set also can be generated. That's enough for finite intersection. This collection has a special name called basis. By basis we can create more topology on a set. Hence if we need a topology on a set, first we have to get a subset collection. There each element is contained in at least one subset of the collection. And intersection between two elements in this collection must be a union of these collections. Instead we can say, if there's an element between intersection of two sets, then we can find an element in these collection containing that element, which is also contained in the intersection. So we can change the second axiom like this. By having subsets like this, we can create open sets, that is topology. Okay, let's see important topology, which is a set containing 0, 1, and between all of those 0 and 1, the basis is of the form like this. This forms a basis. Except 0 and 1, all elements have a known basis elements. But for 0 and 1, we don't have anything before 0 and anything after 1, so every basis element is of the form right side only for 0 and left side only for 1. By basis, it's easy to understand topology for this space. Every element in this set except 0 and 1 has elements in both front and back. It feels like a time moments, where 0 is the start and 1 is the finish. This set looks like a timeline for a video. For a video, we have nothing before the starting point and nothing after ending point. Similarly here, nothing before 0 and nothing after 1. Other than those time moments, everything has a before and after in a video, exactly like 0, 1. So we can define a video as a function from 0, 1 to each frames of a video. Every video is produced by playing pictures one by one with slight variation in a certain amount of time. For example, let's produce a drawing line in 12 FPS, that is 12 frames per second. It means it will play 12 frames one by one in 1 second, so we have to divide the time moment with 12 equal parts, and also the line into 12 equal parts. For 1/12 second, first part of the divided line was played. Until 2/12 second, this frame only be played. That means the set of numbers between 1/12 to 2/12 is mapped to this frame only. After 2/12 second, a frame which is increased in length is played until 3/12 second. Similarly, the function from 2/12 to 3/12 is mapped into this frame. Like this, every other frame's also defined. The machine I am using here also divide the time frame into 12 parts. After 11th part, it will also turns into 1 second. Let's render this video and see what my brain can feel. Ow, my brain can't feel it as a continuously drawn. The length of the line increasing suddenly from nowhere. Let's again produce a video on 60 FPS. Both line and time is divided into 60 parts. Function from 1/60 to 2/60 is mapped into this frame, and also like this for remaining frame. The machine changed to 1 second after 59th part. This is also increasing suddenly from nowhere, so my brain can't feel this as a continuously drawn line. Let's render and see. My brain felt it is so smoothly continuously drawn. I trick my poor brain. Usually human brain feel like this between 30 FPS to 60 FPS videos. Below 30 FPS our brain can understand weirdness. After 60 FPS, our brain can't handle those extra frames, but those extra frames can be used for slow motion videos for clear clarity. By the way, can we make something happening in time loop? We all heard that word time loop. It never ending, also it will have repetition. But at 0, 1 we have a starting 0 and ending 1. We don't need an ending for time loop, so remove 1 from this. 0 has nothing before. So let's assume basis for 0 will have something after 0 and something before 1. By this we are telling 0 has both before and after. That means as the time goes like finishing point, actually it is going for the starting point. We use this in repeat mode. In YouTube Shorts, video doesn't end, it will once again come to the starting point, but we can easily identify those starting and ending, because both are different. Topology of these video frames doesn't make us feel like time loop, because of the different starting and ending. But in some shorts, they will show some frame at starting, then that video will goes to the ending at the same frame. Suppose you have the power to control the timeline of a person and don't know how to create a time loop for a person. First you have to pick 2 time moments you wish to create a time loop. Then remove the last time moment you picked. After that person crossed your first time moment, you have to change the basis element of your first time moment. This will make them stuck on a time. Also, for a time loop, we need a continuous function on this circle. Aren't you curious about how we can define continuous function? Check those in next video.